Power over Ethernet used to be a convenient way to keep a desk phone running. Today, it has become a multi-billion-dollar infrastructure platform that powers massive smart buildings and industrial IoT networks. We are replacing separate 120-volt AC power lines and traditional data lines with a single, unified cable that delivers both power and network connectivity simultaneously. The math here has zero margin for error. Overestimate your power needs and you waste thousands of dollars in excess capital. Underestimate them or apply the wrong voltage, and you will literally fry expensive equipment. A successful deployment depends entirely on matching the exact scale of your project to the right network standard and the right physical architecture. If you are planning a build-out right now, you are probably staring at an alphabet soup of IEEE standards, debating active versus passive voltages, and trying to choose between conflicting architectural layouts. The danger is real. Plug a standard non-PoE device into a proprietary or passive 24-volt PoE line, and because there is no handshake to negotiate the power delivery, the voltage is forced through the cable, permanently damaging the hardware. We are going to clear this up. We will walk through a 3-tier framework to help you specify your PoE infrastructure correctly the very first time. Mastering these tiers protects your physical hardware investment and prevents catastrophic bandwidth and power bottlenecks once the walls are closed up. Tier 1 of the PoE Matrix evaluates power requirements strictly at the individual device level. This device specification chart shows how standards break down. The top row highlights IEEE 802.3 AF, delivering 12.9 watts for basic cameras, but offering zero upgrade headroom. For heavy loads, the third row, IEEE 802.3 BT, pushes 71 watts, a strict necessity for commercial LED lighting grids. Pushing that much power through Ethernet comes with a cost. It requires stringent heat management, especially in thick cable bundles, and relies on significantly more expensive power sourcing equipment. You also need to watch out for 24-volt passive PoE. It is cheaper, but it skips the IEEE negotiation protocols. It pushes power constantly, which will destroy standard non-PoE devices plugged into the same network. Never guess your standard. Open the spec sheet for your specific hardware. This document clearly lists the input voltage range and the exact PoE standard required. That single line dictates your power source. Once you know the wattage, Tier 2 moves to the network level. You have a choice: upgrade your entire network backbone or patch power into your existing lines. This diagram compares methods. On the right, mid-span injectors add power downstream, but at scale, requiring separate data and power cables creates unmanageable rack clutter. On the left, a centralized PoE switch unifies power and data into a single cable per device, providing centralized management. A full switch upgrade demands a high initial capital expense, and it forces you to retire functional non-PoE hardware before the end of its natural life cycle. Your delivery architecture choice permanently dictates your long-term maintenance reality and how easily you can diagnose hardware faults. Finally, Tier 3 zooms out to the macro building level. This is where we route power through ceiling spaces and factory floors for large-scale deployments. The first option is a node-centric topology. In this model, multiple low-power sensors or lights are daisy-chained together off a single primary ceiling node. Nodes drastically reduce your initial cabling runs from the telecom room. However, they limit the total power available per device, and they frequently lock your facility into a specific vendor's proprietary ecosystem. The alternative is a fixture-centric topology. This is a pure hub-and-spoke design, where an individual switch port and a dedicated cable are run to every single light fixture or sensor in the building. A fixture-centric design demands vast pathway space in your ceilings and massive port density in your server racks up front. In exchange, you get maximum remote power delivery and vendor-agnostic flexibility. For enterprise environments, the higher initial cost of all that extra copper in a fixture-centric design pays off by ensuring your infrastructure can adapt to new hardware vendors decades down the line. Before you finalize your architecture and buy hardware, you must calculate the total power budget for the entire deployment. Looking at a standard budget worksheet, we see how this is tracked. The right-hand column lists wattage per port. Remember, a switch's internal power supply cannot run all ports at maximum capacity simultaneously. You must calculate the total accumulative load. Raw mathematics, not marketing promises on a box, will determine whether your entire PoE system actually turns on and stay on under a heavy load. We map these variables into a matrix to lock in your decision. If you are retrofitting an office with a few access points, stay in the bottom left. Do not buy a whole new switch. Use mid-span injectors to patch existing lines. Make sure to check your device spec sheets and match the AF or AT standard precisely, actively avoiding passive PoE unless your specific hardware requires it. If you are an architect or facility manager deploying a building-wide smart lighting grid, jump to the top right. Abandon midspans entirely and invest the capital in a centralized 802.3 BT PoE switch. Deploy that switch using a fixture-centric topology. This guarantees your safety protocols are met and allows future integration between the lighting network and the building's HVAC and security systems. Ultimately, the most reliable PoE architecture is matched mathematically to your specific hardware and deployment scale. Calculate your load, verify your standards, and build the infrastructure your devices actually need.